of electromagnetism by a brief discussion on Maxwell's equations and electromagnetic waves. Now, if you know a couple of laws that we have talked about already, for example, Gauss's law and Ampere's rule, can you recall those two rules or laws? What is Gauss's law for electromagnetism? Gauss's law talks about the net flux that leaves a surface that encloses a certain amount of charge. It says the net flux equal to Q divided by epsilon naught, where Q is the amount of charge enclosed in that surface. Alright, Ampere's rule we discussed in the last lesson. Ampere's rule is about a conductor carrying a current, and if you take a closed path around it, well, the magnetic field in the direction of that closed path, if you take delta L, a small length element, and multiply that with the magnetic field in the direction of or parallel to that delta L, the product of delta L and the magnetic field parallel to it will be equal to the net current within that closed loop. That is the Ampere's rule. Well, both these rules are actually part of Maxwell's equations. So, let's now talk about Maxwell's equations. Well, according to Gauss's law for electric fields, the net electric flux leaving or entering a closed surface enclosing a charge Q is given by integral E dot dA equal to Q over epsilon naught. What does this quantity mean? EdA. Well, if you consider a surface, the E is the electric field at right angles to that surface, and dA is a very small area. So EdA is the flux leaving that element area, and if you integrate that over the surface, that is the net flux. So actually this is the quantity which we generally call the net flux leaving a surface, equal to the enclosed charge divided by epsilon naught, where what is epsilon naught? It's the permittivity of free space, and it has a value 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Now, there are corresponding quantities in magnetism. Can you remember what is the corresponding quantity in magnetism for epsilon naught in electricity? Well, that is mu zero, which is the permeability of free space. So epsilon naught is the permittivity of free space, and remember its value, and mu zero is the permeability of free space. We will use all that in here. So this is the first Maxwell's equation, which is Gauss's law. Gauss's law is Maxwell's first equation. Now, Maxwell's second equation is a similar statement for the magnetic field. So there's a statement for electric field and a similar statement for magnetic field. How can you have a similar statement for magnetic field? Can you have a magnetic poles enclosed inside a surface? Well, you know that magnetic poles don't come in monopoles. They only come in the form of dipoles. So in this case the statement is a little tricky, isn't it? Since there are no free magnetic monopoles, a given space cannot enclose any magnetic monopoles. That means the amount of monopoles that is enclosed in any space will be zero. The amount of magnetic flux entering a closed surface must be equal to the amount of flux leaving it. Therefore, how would you define the second law, second Maxwell's equation? which is analogous to the Coulomb's law in electricity. If you translate that into magnetism, it becomes the second law of Maxwell. Therefore, the net flux out of the enclosed volume is zero. Why is it zero? Because the net poles, monopoles enclosed in that surface is zero. And therefore, the second Maxwell's equation is integral B dA. What does B dA stands for? Well, B dA is the flux that leaves a small area dA, and you integrate it over the entire surface. That is the net magnetic flux leaving that surface, and that is equal to zero, is Maxwell's second equation. Now you notice that Maxwell's first and second equations involve integration over a surface. In other words, the total flux that leaves a surface. Now the first two Maxwell's equations given above are for integrals of the electric and magnetic fields over closed surfaces enclosing a volume. That we just talked about. The third and fourth Maxwell's equations are for integrals of electric and magnetic fields around a closed curve. Well, are you familiar with integrating around a closed curve? We just talked about it, Ampere's rule. If you have a closed path around a conductor, we said the product of the length element delta L times the magnetic field parallel to it. And if you add up all such quantities, and that is what we call the line integral, integral around a path. So the third and fourth Maxwell's equations are for integrals of electric and magnetic fields in closed curves. Now, we take the component of the field pointing along the curve. Now, that is very important. If I can find a curve, let me see if I can find a curve. Now, here is an example of a closed path. If I take a small element of this delta L and multiply that with the component of the magnetic field in the direction of it and add all such products along the length, that is the line integral, total line integral. So we take the component of the field pointing in the direction along the curve and calculating the line integral in order to calculate EdL or BdL. In the case of the electric field, we take the component of the electric field along the dl. In the case of the magnetic field, we have the magnetic field along dl. So we have EdL or BdL and integrate it along the curve, and that is the quantity we will be using to describe the third and fourth of Maxwell's equations. Now, these line integrals represent the work that would be needed to take a charge around a closed curve. Well, so EdL is a measure of work done to take a unit charge around this closed path. Alright, now the simplest version of Maxwell's third equation is the electrostatic case integral. Now remember, this integral stands for the line integral. The earlier two integrals we did for equations 1 and 2 are surface integrals. So line integrals E dot dl equal to 0. In other words, this is the equation similar to Ampere's rule in magnetism. And this is Maxwell's third equation. And a similar line integral in a magnetic field is the Ampere's rule, which we talked about. In other words, delta L times B integrated along the length of the curve is a measure of the amount of current inside the loop. So the magnetic field in a space around an electric current, the magnetic field in a space around an electric current is proportional to the electric current which serves as its source. In fact, the magnetic field is actually created by the current in this conductor, just as the electric field in space is proportional to the electric charge which serves as its source. Now, Ampere's law states that for any closed loop path, that's a closed loop path, the sum of the length elements times the magnetic field in the direction of the length element. One more time, if you take that length element delta L and take the component of that B in the direction of that delta L and multiply the two, B delta L, and integrate it along the closed curve, it will be equal to the permeability times the electric current enclosed in the loop. The electric current enclosed in the loop will be I. And we write it like this: line integral B dl is mu 0 times the net current within the loop. And that is the fourth Maxwell's equations. So here, I net is the net current passing through the surface bounded by this closed path. Alright, however, this equation requires a little modification. And I have written the equation on the top. Why? Consider a closed circuit path where a capacitor is being discharged. Now, there is a magnetic field around the wire. There is a magnetic field around this wire only when electric charges are flowing away from the capacitor plates. When the electric charges are not flowing, there is no magnetic field. Now remember, magnetic fields are created only when electric charges are in motion. The changing charge on the plates means that when the capacitor plate is discharged, the charge on the plates is changing. So the changing charge on the plates means that the electric field between the plates is changing. So the electric field between the plates is changing and the magnetic field around the wires are also changing. Now Maxwell proposed that there needs to be an extra term on the right in Ampere's rule. Now the right side of the Ampere's rule is mu 0 times I net, net current within the loop. Now Maxwell suggested that there needs to be an extra term there involving the changing electric field in such a situation. Now, if V is the potential difference across the capacitor plates, the charge Q can be written as Q equal to CV. There's no problem there. C is the capacitance and V is the potential difference. Now, if E is the electric field between the two plates, you know that V equal to E times D. Is that right? That's the way we have been defining potential difference between the two plates, where D is the distance between the plates and E is the electric field inside the plate. Now, for a parallel plate capacitor, can you recall what's the capacitance of a parallel plate capacitor? Its capacitance is epsilon naught A over D, where of course epsilon naught is the permittivity of free space, A is the area of the capacitor plates, and D is the plate separation. And now all these things we discussed, those three equations, I have brought it back with me. And now this gives Q equal to epsilon naught A over D times ED. Q equal to CV, is that right? Where we replace C by epsilon naught A over D and V by E times D. And of course the D and D will cancel. That gives you epsilon naught AE. That is Q, that is the amount of charge on the capacitor plates. Now, if you now take the derivative of this with respect to time, we get dq by dt equal to epsilon naught A dE by dt, because as the amount of charge in the capacitor plate changes, the electric field also changes. Now, what does dq over dt represent? dq over dt represents the current in the wire. Is that right? The rate at which the charges are flowing. So, you got I equal to dq by dt, which is therefore epsilon naught A dE by dt. And this can be written as, look at the way I rewrote it. I wrote it as epsilon naught d by dt of the net flux within the capacitor plate. Why? Because area times the electric field is a measure of the total flux, isn't it? The electric field is the flux per unit area. So A times E is the net flux. So A times dE by dt is simply d phi by dt. Now, this current is not caused by the flow of charges, and Maxwell called this current the displacement current. And it is this quantity that Maxwell said should appear on the right side of that fourth equation. So this is the extra term that needs to be added to the right side of the Ampere's law involving changing electric field. Now, thus the general form of the Ampere's rule now becomes line integral B dl is, so in place of mu 0 times I net, that I net is now modified along with this net current is the displacement current. So I net plus epsilon naught d phi by dt is now the total current. So the Ampere's rule now becomes line integral B dl is mu 0 times the total current, which is the net current in the conductor plus the displacement current. Well, therefore, let's now write down the four Maxwell's equations. What is the first equation, Maxwell's first equation? Well, of course, it's Gauss's law. Surface integral EdA equal to Q over epsilon naught. The net flux that is crossing any surface is the charge inside the surface divided by epsilon naught. And a similar equation for magnetic field is, if the net flux that is crossing any surface, net magnetic flux that crosses any surface is equal to 0 because it cannot enclose any magnetic monopoles. The third equation is line integral E dl is d phi by dt. And the fourth equation is line integral B dl is mu 0 times I net plus epsilon naught d phi by dt. These are the four Maxwell's equations. Let's now take a few minutes to talk about electromagnetic waves. Now, what do you know about electromagnetic waves? Well, everything that we do, including the video that I'm doing, is made possible because of electromagnetic waves. Light is a form of electromagnetic waves. Well, let's talk a bit about that. A changing magnetic field produces an electric field. Is that right? It is a fluctuating magnetic field that generates an electric current. So a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. I have told you this even before, that I have misspelled fields several places, so ignore that. Now, the magnetic and electric fields are perpendicular to each other. If the electric field is propagated in the horizontal direction, magnetic field will be propagated in the vertical direction. And both these fields are actually alternating. that's in the form of transverse wave. The net result of such interacting changing fields is the propagation of orthogonal electric and magnetic fields in space. Now, what's the meaning of orthogonal electric and magnetic fields? Well, orthogonal, of course, means perpendicular. That means if the magnetic fields is propagated horizontally, the electric field is propagated vertically. These two fields are perpendicular to each other. Now, this phenomenon is referred to as electromagnetic waves. So what is the phenomenon of electromagnetic waves? Electromagnetic waves are simply propagation of electric and magnetic fields which are at right angles to each other. Now, electromagnetic waves are transverse wave whose wavelength lambda is measured from crest to crest, that is from maximum of electric or magnetic displacement. You are familiar with transverse waves. So when you talk about the maximum of the wave, it could be the maximum displacement for electric or magnetic fields. Now here I have an illustration of that. The magnetic field, if this is the magnetic field, that is the electric field. So the magnetic field is the horizontal vibration and the electric field is the vertical vibration. And look at the direction of propagation. The direction of propagation is at right angles to both these. So if this is the magnetic field, suppose we call this x direction, and the electric field is in the z direction, then the direction of propagation is the y direction. Is that right? If this is x and this is z and this will be y, you can actually orient it in any way you want. The most important thing is the magnetic fields, the electric field, and the direction of propagation are mutually perpendicular to each other. I have another diagram here. Here, this is the magnetic field. The blue line, well, that is a horizontal wave, and the red wave is the electric field, which is vertical, and the direction of propagation is at right angles to both these. The magnitudes of E and B are in phase. What does that mean? The magnitudes of B and E are in phase. When the magnetic field reaches a maximum, the electric field also reaches a maximum. When the electric field is zero, the magnetic field also is zero. So the electric and magnetic fields are in phase, and look at the equation that they are related by. They are related by E equal to CB. Electric field equal to C times B, where C is the speed of electromagnetic waves in space. Where C is the speed of electromagnetic waves in free space and can be expressed in terms of, now I want you to pay attention to this and appreciate this very important and interesting concept. C is the speed of electromagnetic waves in free space. Epsilon naught is the permittivity of free space, and mu zero is the permeability of free space. You can see here electric property, magnetic property, electromagnetic property. So C is the speed of electromagnetic waves, and this speed can be expressed in terms of this epsilon naught and mu zero, like this. C equal to 1 over square root of mu zero times epsilon naught. Now, isn't that interesting? If you know the values of mu zero and epsilon naught, which you know, alright, how many of you can tell me what is mu zero? Well, mu zero is 4 pi times 10 to the negative 7. Epsilon naught is 8.85 times 10 to the negative 12. Well, all forms of electromagnetic waves travel in free space with the same speed c. Now, how many forms of electromagnetic waves do you know? Well, we've got radio waves, infrared, visible light, the lights that we see, ultraviolet, X-rays, gamma rays. They are all electromagnetic waves, and they all travel in space with the same speed c, and the value of c can be computed from the values of mu0 and epsilon naught. Replace mu0 by 4 pi times 10 to the negative 7 Tesla meter per ampere, and epsilon naught, the permittivity of free space, 8.85 times 10 to the negative 12 Coulomb squared Newton per meter squared, and that gives you c equal to 3 times 10 to the power of 8 meter per second. Now, this is an important constant, and according to Einstein, nothing can travel faster than this, right? Okay. How about electromagnetic spectrum? Electromagnetic spectrum is actually a collection of all forms of electromagnetic waves. Now, I think in the discussion on thermodynamics, we talked about the radiation that are emitted by all objects. All objects at all temperature emits radiation in the form of electromagnetic waves. Now, electromagnetic spectrum, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays, are all electromagnetic waves of different wavelength and frequencies. Now, all these range of waves or radiations put together is called electromagnetic spectrum. The wavelengths of these radiations vary from about a kilometer for radio waves, radio waves themselves range from few kilometers to few millimeters, short waves and long wave radio. Now, so vary from about a kilometer for radio waves and a few picometers for very high energy gamma radiation. These gamma radiations are so short they can actually penetrate through you without even knowing. Now, the speed of electromagnetic waves can be expressed in terms of their frequency and wavelength. Well, all forms of waves are described by this equation, c equal to f lambda. So we got actually two equations for speed of electromagnetic waves. One in terms of mu0 and epsilon naught, the other in terms of the frequency and wavelength. Now, here is a rough picture of electromagnetic spectrum. If you start from the left, you got radio waves of wavelength few kilometers, and you go to the right, the wavelength is steadily decreasing, and you come to microwaves. Well, all these are radio waves, long radio waves to short radio waves. Then you have a range of microwaves, you have radars, infrared, which are heat rays. So the wavelength is steadily decreasing. And look at the visible light. Visible light is a very small part of the electromagnetic spectrum. And how many different types of waves are in the visible region of that? It's over 3,000 different waves. Well, then comes to ultraviolet, we got X-rays, gamma rays, and so on. So the wavelength ranges from, say, 10 to the power of 3 meters to about 10 to the power of negative 12. That's the one I talked about, a picometer. Now, the frequency of radio waves, say, it's about 10 to the power of 6. Now, as the wavelength decreases, the frequency will increase. And the energy, well, a radiation carries energy. The electromagnetic radiations can be considered to be particle in nature, and we call those particles photons, and the energy of the photons are also listed there. The energy steadily increases as the frequency increases. You can see the energy is given in electron volt. An electron volt is the energy acquired by an electron when it is accelerated by just 1 volt. So you can see the energy of a radio wave photon is 10 to the negative 9 electron volt, 1/1000th of an electron volt, very small energy. While the energy of a gamma ray photon is about 1,000,000 electron volt, a big difference in the energy. So you must have a rough idea on electromagnetic waves, their relative wavelength to frequencies and energy values. Visible light consists of over 3,000 different frequencies, and each frequency corresponds to a color. So how many colors are there in our visible light? There are over 3,000 different colors. Well, the perceived colors, very often people talk about 7 colors, the rainbow colors. They are the perceived color, like red, orange, yellow, green, cyan, blue, and violet are actually combinations of many hundreds of wavelengths. Now, for example, red is a combination of wavelength from 625 to 740 nanometer. Now, blue color that we normally see as blue is a combination of wavelength that range from 435 to 500 nanometer. So it's a combination of about 65 different wavelengths. Alright, let's do an example. Find the wavelength for a radio wave of frequency 1000 kilohertz, a radio wave of frequency 100 megahertz. It's a very simple problem because you know that the speed of all electromagnetic waves is 3 times 10 to the 8 meter per second. And we also know that speed is related to frequency and wavelength as c equal to f lambda. So to find the wavelength, we solve for lambda here. Lambda equal to c over f. So in the first case, it will be c divided by 1000 kilohertz is 10 to the power of 6 hertz. And that is 300 meter. The wavelength of that wave. In the second case, the frequency is 100 megahertz. Well, 100 megahertz is 10 to the power of 8 hertz, and that wave has the length of 3 meter. As the wavelength, as the frequency increases, the wavelength becomes shorter and shorter. Second, what is the frequency of a 1.2 centimeter microwave? Well, again, solve for frequency and use the given values, and that is 1.56 times 10 to the 10 hertz. Next, we will briefly discuss energy and momentum in an electromagnetic wave. These waves carry energy with them. The propagation of electric and magnetic fields results in the propagation of energy. Now, this means that electric and magnetic fields carry energy. Now, the electric energy density U sub E of the electric field E and the magnetic energy density U sub B of the magnetic field B are given by the expressions. We actually discussed them briefly before, if you recall. And these expressions are U sub E, which is the electric field, electric energy density, is 1/2 epsilon naught E squared And a similar expression for magnetic energy, U sub B, that is the magnetic energy density, is B squared divided by 2 mu 0. I think we discussed these in our last lesson. Now, since E equal to CB, remember that? We can actually modify these equations. Suppose we replace our B by E divided by C here. Can you do that? Replace this B by E divided by C. What will that become? UB become E squared epsilon naught mu 0 over 2 mu 0. Is that right? Well, did you see how that was obtained? Well, we replaced B by E over C, and our C is 1 over square root mu 0 epsilon naught. I want you to do that on your own and see whether you come to this. You can see UB therefore also is 1/2 E 0 epsilon naught E squared. That means if you replace B using E equal to CB by E over C, you will see UE and UB really have the same magnitude. So, the energy density is the same for both E and B. That's what we just showed. The total energy density, therefore, of the electromagnetic wave U is the sum of the two, UE plus UB. That is 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared is epsilon naught E squared. And you can write this also as B squared over mu 0. Epsilon naught E squared and B squared over mu 0 are both the same, using the relation E equal to C times B. And of course C equal to square root of mu 0 times epsilon naught. Okay. Now the average energy density can be obtained by replacing E and B by their RMS values. So if this is the energy density for an electromagnetic wave, EB divided by mu 0 C, what is the average energy density? It will be E RMS times B RMS over mu 0 C. Now this average energy is a measure of the momentum P carried by the wave per unit time per unit area. Now that's an important concept. Alright, so the average energy E RMS, B RMS over mu 0 C. Now what is the meaning of intensity of a radiation? We talked about in connection with our discussion on waves, intensity. Now, if there is a radiation that is emitted, for example, I'm standing in front of a projector and the light that is falling on me is from the lamp of the projector. That's why you see my shadow on the board. Now, what is the measure of the intensity of that radiation? Well, in order to define the intensity at a particular point, what we do is we keep a unit area where we want to find the intensity. It is the amount of power crossing at right angles to a unit area is what we call intensity. So intensity is a measure of the power crossing unit area at that particular place. Now if I move this unit area away, the amount of power crossing that unit area will be now less. That means as you move away from the source, the intensity will become less and less. Alright, so the intensity I of a wave is defined as the product of wave speed and the average energy density. Well, having known what intensity is, we can make use of that definition. In other words, Intensity I is the product of the wave speed c and the average energy density. So I can now write it as c times the average energy density is E RMS B RMS divided by mu 0 c, and that will be E RMS B RMS divided by mu 0 because the c's will disappear. Now, the intensity divided by c is the force per unit area. What's force per unit area called? Force per unit area is called the pressure, and therefore the radiation pressure, whenever radiation falls on a surface, there's a radiation pressure. And how do you calculate the radiation pressure? It is the intensity divided by c. I divided by c is radiation pressure. So P sub r, the radiation pressure, is intensity I divided by c, the wave speed, and that is equal to U is E RMS B RMS divided by mu 0 c. In other words, this is I. If you divide that by c, you get mu 0 c on the denominator. So that is an expression for the radiation pressure. You can also write it as E max squared divided by 2 mu 0 c squared. Now, how did that come about? Can you picture that? Well, E equal to CB. So B equal to E over C. And that is where the E squared comes in, and the C goes to become C squared. Is that right? Replace this B by E over C, and you get that equation. So the radiation pressure is E max squared divided by 2 mu 0 c squared. And that can also be written as B max squared over 2 mu 0. How? By replacing E equal to CB. Alright, let's do a small problem. A 50-watt electric light bulb emits spherical electromagnetic waves in all directions. Find the intensity of the waves. Well, this is where the original definition of intensity is going to help. What is intensity definition? It is the power crossing unit area at that point. That's how we're going to calculate that intensity. The radiation pressure and the electric and magnetic fields at distances 3 meters from the bulb. Well, in fact, I'm standing about 3 meters from the bulb, and this problem is very much applicable in my case. What is the radiation pressure on my face? What are the values of electric and magnetic fields where I'm standing? Well, the intensity I at a point is a measure of the power per unit area at that point. Is that right? So, I equal to 50 watt divided by 4 pi r squared. In fact, that's the bulb about 3 meters from there. That's the distance r, and you can see if I construct a sphere of radius r, the total power that is going out of that sphere will be, that's the total power. If you divide by 4 pi r squared, which is the area of that sphere, that will give you the power per unit area. I hope you understand that. If I have the lighted bulb here, if you take a surface of radius r around it, the area of that surface will be 4 pi r squared. So if you want to find the intensity at any point, divide the total power, which is the 50 watt given to us, by the total area, which is 4 pi r squared. So intensity I is power divided by the area, and that will be 0.442 watt per meter squared. Once you know the intensity, we can find the radiation pressure. What's the definition of radiation pressure? Radiation pressure is intensity divided by C. So P sub R is I divided by C, and we know those values. That gives you 1.47 times 10 to the negative 9 Pascal is the radiation power. Well, we now need to find the electric and magnetic fields where R equal to 3 meter. And for that we go and select this equation. We had obtained several equations for the radiation pressure in terms of electric field and in terms of magnetic field. So we are now going to use the equation in terms of electric field. PR is E0 squared divided by 2 mu 0 C squared. And we know all these values. Therefore, E max, well, E max is the same as E0. But E0 squared is 2 PR mu 0 C squared. Therefore, E max is the square root of that quantity. And use all those values. We just calculated the radiation pressure. We know mu 0 and we have C squared. That gives you E max, the maximum electric field is 18.2 volts per meter. Now, in the same way, you can calculate the magnetic field. I think I'm going to leave that for you and go to another problem. The amplitude of an electromagnetic wave is E max equal to 140 volts per meter. Find E RMS, B RMS, the intensity I, and the radiation pressure P sub R. Well, they're all direct applications of the formula we have. E RMS is E max divided by square root of 2, and we have E max. Therefore, the RMS value of that voltage is, of that field is 99 volts per meter. Now, B RMS is E RMS divided by C. Is that right? Yes, because E equal to CB. So since we have E RMS, B RMS can be calculated as 0.33 micro Tesla. Now, radiation pressure, the intensity is E RMS, B RMS divided by mu 0, and we have both these values, and that gives you the intensity as 26 watt per square meter. And what else do we need? The radiation pressure. Well, we have the radiation pressure P sub R equal to I over C. We have I and we know C. That is 8.7 times 10 to the negative 8 Pascal. Well, simple problems, but you must be able to recall all these equations. Well, and that is the end of our discussion on electromagnetism. And I think in this unit I'm going to include a lesson on light, because it's very appropriate. After we discuss electromagnetic waves, light is a form of electromagnetic waves, so we spend at least one lesson talking about electromagnetic waves.